Swayam Prabha. Digital India. Educated India.
So good morning, everyone. First of all, I wish to thank Professor Ratana and the Gen School to offer me this opportunity really to give this Gen course work. And there is as Professor Ratana mentioned before, it's quite unfortunate that I couldn't get my visa timely. So we have to really switch my lecture part online. Today, I will have a quick introduction to this computational granular material, which is a supplement to what Professor Ratner just mentioned in the first part. Okay, and so I just introduce more examples from the civil engineering point of view, and in addition to that, and to other part, and then to give motivations that why we have really to study granular material, and what kind of computational tools that we can make use of, and what are the challenges. So this is the purpose of today's introductory lecture. And so, first of all, as Professor Ratner mentioned, that granular material is everywhere in our daily life. Indeed, granular material are the second most processed material in industry. Of course, the most one is water. Okay, and then as you can tell that from our daily life, and then we encounter granular matter everywhere and every time here, from the coffee, sugar, salt, and the food grain, medical tablets, and everything here. Okay, so when we want to really study granular material, it's important and it's very useful as well here. Okay, I have a quick introduction about why it's important granular material, and it's basically most visually that found that are important to our civil engineering in the way that when we see this World Heritage buildings from everywhere, including India, China, and also from Egypt, from Greece, and then how to really make this heritage building stand there for so long time, and we need to understand the fundamental mechanical behaviors of granular media. Okay, including the media that we choose to really to build, like this, the Great Pyramid of Khufu, and also like the foundation that have to build it. So this is from the World Heritage. Yeah. And now to the modern buildings, and you can imagine that we have a high-rise building of several hundred meters tall, and then you can imagine that how strong that we need a building foundation. And those foundation, no matter what kind of foundations that are shown here, the foundation can be tall, not as tall as the superstructure have, but this foundation will mostly be transferring the superstructure load onto the surrounding soil, and those soils are typical granular material. And then we need to understand their behaviors in order really to design and maintain a safe structure like this one here. So in data, granular media is everywhere as we see that in the remote area that are in the mountains, in the even sea ice, and ice are considered granular media, and also the dust storm is considered another type of granular media. Of course, the sand, the desert, is a typical granular media. And then to our daily life, for example, if we go to the beach, we play sand, and then these are the quite fascinating phenomena that we can observe in the typical granular media sand here. Okay, we add a little bit of water, and then apparently a quite loose sand can really stand tall as a sand castle. These are the quite fascinating behaviors that we encounter here. And also, granular media can be quite disastrous, as I showed on the left, that the very large scale landslide happened in Taiwan. On the right is it's a snow avalanche, and the snow itself can also be considered a typical granular meteor, as I showed here. When such a large scale landslides happened, then it can cause quite a disastrous consequence. And this is another very recent example. So this is a rock as mixture avalanche of debris flow happened in Switzerland in last May, and then it was caught in the camera, and then it triggered a lot of interest in how really to simulate it by different computational method, and so how to really to develop a methodology to really to as a early warning system really to prevent further future injuries or damages to human and property. And also in the coastal engineering, when we develop a different infrastructure, when we do dredging, and then we want to develop a so-called the breakwater for coastal protection, and we need to consider this artificial structure and can also be considered a special type of this granular meter. And when we want to consider their performance, and we can model it. Okay, and also on the seabed, rare minerals explorations, and those things can also be considered early granular meter here. Of course, and when we consider offshore infrastructure like an oil platform, when we design that to resist all kind of like a wave load and wind load, we need to consider the bearing capacity of the seabed soil, and this again is related to the granular meter here. And then to mining engineering, and is everywhere that we have to deal with granular meter, like when we excavate the mines, and then when we crush it, and then when we use conveyor belt to transport it to certain places, or when we do blast, really to blast the intact rock, and then to extract the minerals here. These are the mining engineering applications of granular meter here. And then in our daily life, we take a trains. This railway engineering is closely related to granular meter. When we design a railway track, we have to consider how the surrounding soils that are support this track and give you sufficient and sustained bearing capacity that can hold the repeated the train load up to this railway track here. And then in agriculture, and then the soil itself causes granular meter, and also this food grain itself, food grain and fruit, those are all can be considered granular meter. That if we want to know their performance in every aspect, and then the study of granular meter can be important here. Of course, when we will collect this food grain and then want to pack it, or we want to store it, and then we need to design proper storage silos and other things for purpose. I think this is the one example Professor Ratna previously showed that improper design of these silos can really cause disastrous consequence here. And also in advanced manufacturing, especially now, and when we really involve a lot of we want to design this 3D printing technologies, and then we want to use a high energy laser or other thoughts ready to melt the metal powder and into certain advanced complicated products like a rocket engine. And then this granular meter can be the key part how we can relate to understand the printing process, optimize this printing process as well, and also try to test the performance of this products before we actually print it out here. as Professor Ratton mentioned before, that in pharmaceutical industry that we have really done a lot of medical tablets, and then to test the performance of the tablets, and also different shape. Cause shape itself is important for the comfort of using usage. For example, when we want really to swallow a tablet, you want really to design a proper shape that can help you to swallow it and smoothly. And also the shape itself can also related to how soon this tablet can be solved in your stomach, and that's also important related to for the effect of this medicine. Those are all things related to granular meter, and then is indeed one of the many important active areas that are in the granular meter research. And then granular meter can be found related to this Earth exploration. For example, now people wanted to dig deep in the Earth crust, ready to extract the rare earth mud or other minerals from the seabed, from the deep ground here, and also want to study these carbon cycles and from the different depths of this ground. And then this is deep earth exploration and deep sea explorations. We have a lot of challenges and needs to study granular meter and to understand its performance here. And out of this Earth, and then we have, as Professor Barton mentioned before, that we have a lot of countries around the world that have ambition really to explore their other planets, like the Moon, the Mars, and then the first important thing was how we can really to land a man-made rovers and other explorers ready to other planets. And then so the first thing is how can make our landers land there on the Mars and the Moon safely in the first place, and then further on, if there's in future opportunities, then we can really transport a human being over there. This is other planetary explorations. A lot of challenges going on. For example, not only that, for example, such a lander on the top can land safely, and then, but also during the landing process, the engine will eject a lot of kind of the dust and flares, and then how this interact with the dust on the Moon and the Mars, and then how would that try to avoid the adverse effect of this dust with these landers or rovers, and these are important parts that we have to really to deal with granular meter research here. And so other Professor Ratana defined before that granular meter is basically referred to a aggregates composed of many mutually contact particles. And the void included by these particles as shown in the following example. It sometimes called granular meter, granular material, soft matter sometimes, and also in a general sense is belong to a condensed matter here, right? And then a granular meter is very challenging to understand. The show here, I quote the 1991 Nobel laureates, PLG's the genius. It said that the fundamental research in granular meter has been appreciated in mechanical engineering for a long time here. Okay, but they show a quite complicated state, for example, transition from a solid lag to a fluid lag or vice versa, and then there's no consensus to really to describe it and totally really, for example, to model it. Okay, and then he concluded that the granular meter, the understanding in 1998, as he wrote this review paper, is still at the same level of solid state of physics in 1930. Okay, so there's much that we can do to explore to work on the granular media research here. Okay. And there are many other complex phenomena that exhibited in granular matter. As I showed, as I mentioned, the solid liquid lack of phase transition, and in terms of the traffic jams, landslides, other things that are all the actually a real shape, a real form of this phase transition types here. And also arching in the sand dune, okay, and this is pretty much related to how we can relate to design, for example, shallow and other part here. And also the shallow effect, and then the wall friction can cause pressure, and then sometimes it cause jamming other part here. And also the shear induced liquefaction. This is pretty much a phenomenon that are related to geotech engineering. If you in the earthquake active regions that are a sandy soil foundation can be liquefied because this earthquake shearing force ready to cause some kind of like we call it in some kind we call it the loss of effective stress and strength, and then the bearing capacity of certain soils are totally lost here. And also the vibration induced segregation pulp. This is one of the expertise of Professor Ratna. And then we want to do all kind of like a different vibration load and other load, and we find that different size of particle will segregate to apparent different height of layers here. Okay. And also there are other physical experiments that we can relate to show the fascinating phenomena observed in a granular media. And so those are the things that, just to give you some example, for example, we mentioned this solid liquid lack of phase transition here. And we can power we can form a sun pile, stable sun pile like this here. And then when we ready to put in the cello, and then it become liquid layer. Okay, and then indeed, and we can really to observe a transition, for example, a gas look, liquid look, and a solid look. When we ready to when we ready to have a sliding cases. Okay. And so this is a typical showing of this solid liquid phase transition here, okay, as one example here. This is give another example here, okay, and this is a moving some kind of minerals and things here. And then this is another example, a typical example how we can really to easily change a solid like granular meter and to a liquid lag. Okay. And so this whole thing has been studied for a long time, and it is understand that the false transmission mechanisms underlying this like solid and liquid lag phase transition, and this is what we call strong and weak force network observed by Bob Beringer and using his photoelastic experiment here. And so those are light and strong chain-like structure we call strong force chain. Well, those background weak one are the weak force chain here. Okay, and the strong force chain is supposed really to support the major shear force, while the weak force chain is supposed to resist the hydrostatic pressure. And these two basically to support each other, but when this strong force chain is barcode, and then all the weak force chain network is weak enough, and then this will change the granular media state from a solid to a liquid. So this is the observation here. This is a further examination. If you continue to shear it in a range shear test, and then you can also did this the continuous intermediate buckling, and re-establish of this strong force chain, and then doing this shearing process here. And then that's why that the Granular has been released by Science in on his 125th anniversary as one of these 125 questions unanswered here. Okay, so the specific question to be still unresolved is can we develop a general theory of the dynamics of turbulent flow and the motion of a Granular. Okay, and then so far we are such a non-equilibrium system basically cannot be modeled and understood by any statistical mechanics. And then there's a strong gap and that waiting for us to fill here. Okay, and for example, the general question is can we develop an integrated theory of turbulent dynamics and Granular mechanics? Okay, so that is I think you guys stating there, and it's a really exciting topic if you are interested in Granular physics, and these are the Granular challenges that you can really tackle on to work on here. Okay. And I'll quickly introduce briefly some fundamental characteristics of Granular. First, the physical characteristics. And so Granular, their grain size and shape matters here. They roughly plot the size range here. We call Granular generally, in a general sense, that if their grain size is in between of this 10 to the power 4 meters and to up to 1 millimeter. And then if we call the polar, if their grain size is between 100 microns to 100 nanometers. And then we further call it nanomaterials, and then it is below 100 nanometers here. Okay, so grain size and shape matters here. First, grain size here, and from 7 engineering point of view, that we could really sort out the soil particle size ranges and to use a different we call a sieve shaker, and we basically put different sieves here to really to allow the small particles falling down from the top sieve to the bottom sieve, and then the big particle will live in a corresponding passing side here. Okay, and then from that kind of test, we can identify that we can give a terminology that if the size is greater than 5 millimeters, we call it gravel, and then if it is between 74 micron to 5 millimeter, we call it sand here, and then between 2 micron and then with 75 micron, and we call it silt, and below than that, and then we call it clay. So these are according to the soil mechanics classification here. And if you want to have a direct comparison of what is the typical size of sand and clay, and so a typical size of sand needs to compare if we use use a barrel like in a vineyard, the barrel hold this one, and then that is the size of sand here, and then comparatively the size of the silt particle will only like a dining plate size, and while the clay particle is only a small coin that size here, and so grain size can really to vary from a very large range here. And then according to the particle size in geotech engineering, and they give different classification of this size here. Of course, the soil is not uniform. Particle size is composition of a different size here. For example, different content of the clay, different content of the sand, and different content of silt will give you a different combined name. For example, in the middle, we call it sandy clay, or we call it silty clay here, and we call loam, and if the composition of the three are in this range here. We can plot the different soil using the so-called grain size distribution curve like this one. Basically, vertical is a fine content, a cumulative fine content, and then the horizontal is the particle size or particle diameter here. Okay, and so the left and right basically give you a different average size. Here, left is definitely average size of finer. For example, it's indeed indicate a shield volume, and shield volume is in this range here, right? And then on the right is basically is a sand grain size distribution here, right? And if you find a grain size distribution and their slope is very steep, and we call is poorly graded, and but is relatively flat, and we call it well graded. And those all things, the grain size distribution will affect the overall properties of a granular media here. And also the other thing would be this green shape. And then as I showed on the top top right corner, and this typical SEM picture of the of sand particles here. And typically we use different shape descriptors to describe the green shape. For example, the flatness, angularity, roundness, and roughness here. Okay. And but in a quite a popular way that we use a 3-dimension to define it. We use L to indicate the longest dimension of a particle, like this one here. Okay, we use I to indicate the longest dimension, which is perpendicular to the L and S direction, and then S is the other direction, which is perpendicular to L and I here. Okay. And then, according to the different ratio of I over L or S over I, and then we can plot such kind of the shape triangle or texture or shape texture of particles. And the indicator is whether or not it is elongate or whether or not it's flat here, right? So those are the different quantitative descriptions of the particle shape, grain shape here. And here, this is what I generated according to the different ratio of the I over L. On the top, you can see here is a perfect sphere, and then so the ratio is always both ratio are 1 here. We get a sphere here. And then if you move it down, and you can apparently see their shape will change significantly as I showed here, right? And you can see here on the left corner, and this could be a little bit of ellipsoid here, but this one will give you a needle-like particle shape. And so in natural settings, like in a natural sand, and we could really find a different grain shape. The grain shape indeed matter a lot in many aspects of the granular media behaviors. So in addition to the grain size and shape, there are also geometric measures of granular media. I just quickly introduce, for example, there are isotropic geometric measures, and the overall bulk measure, and we can define the void ratio as the total volume of void in the assembly over the void of the solid. Or the solid, for example, particle volume, and this is defined as E, we call it void ratio. And then we can also define other quantities more or less equivalent. We can really to translate them between them here, such like the porosity is defined as a volume of void and over the total volume of this assembly here, and we normally denote N here. And also the solid fraction, or sometimes we call it solid density. And then we use the volume of solid over the total volume here, right? And also in solid mechanics, and then we use another density, we call it relative density, to define in this way. And for a certain solid, we can experimentally determine the loosest, or E max, the void ratio, maximum void ratio, and also the densest, we call it E minimum, okay, and the minimum void ratio. And so if we measure the carbon void ratio of a solid, we can define this relative density to quantify its state, and then give you a rough like that how loose or dense this solid would be. And their density will matter a lot to their mechanical response here. And of course, we can define a unit weight, okay? And also for solids, and in some kinds, we define a lot of different density, including moisture, different unit weight, a moisture unit, in the saturated unit weight, effective unit weight. But I won't really go that in detail here. That is the isotropic geometric measures, and then we could also define some anisotropic geometric measures here. Indeed, this word anisotropy is a very important characteristic of granular meter. And in some kinds, back in 1984, Casgrande and Carrillo and divided the anisotropy into two different sources. One is called inherent anisotropy that you can see on the right here. And if we go to the page, and then if we dig a little bit and then create a vertical profile, and we can observe that the sand will be formed in this will be formed in this layer structure. Okay, and this is a very good example of this called inherent anisotropy. It's basically referred to a physical characteristic which is inherent in this material and independent of the applied strain. It has been there without external force here, right? And then another type of anisotropy is called induced anisotropy. And so I showed on the right, basically, again, is a photoelastic results by Bob Ranger. And use this, you shear the particle assembly from the top, and then it form a strong force chain. And this strong force chain, in contrast with this background weak force chain, will give you quite clear induced anisotropic structure. It's basically this is a characteristic due to this strain associated with this applied stress here, right? And then how to really quantify the anisotropy, and people developed a so-called granular fabric to quantify it. And then the granular fabric physically can be understood as the arrangement of particles, particle group, and Paul space here. Okay. And for example, on the right, I listed the typical granular fabric and found in soils. And for clays, and we can have individual clay platelet, and then they can interact with the diameter waste and then form a relatively isotropic structure or more anisotropic structure, right? You could also have this clay platelet group and interact with each other in this way here. Or you have student or sand particles and interact according to this interparticle contact here. Okay. And also in the natural settings, the coarse particle surface can be surrounded by the fans, and fans will interact with other particles in such a complicated way here, right? And so also in a lot of literature, and we refer to a term we call internal structure. An internal structure is not purely geometric. Indeed, its internal structure normally is understood as a combined effect of fabric, composition, and the internal particle forces. So they involve the particle forces in this internal structure here, right? So these are the granular fabric. And then also for inherent anisotropy, and back in 1989, Oda and Nakayama, they argued that there could be three sources of anisotropy. And the anisotropic distribution of contact normal, you have particle contact with each other, the contact normal will change in different direction because you have so many contacts here. And this will be indicative factor of this the mutual relation among the particles. This is the one source of this anisotropy. And also the other side is the preferred orientation of the non-spherical particle, non-spherical void. So void also play a role in this anisotropy here. And also there will be preferred orientation of non-spherical particle here. Particle shape matter in this case here. And in that way, how we can really quantify our inner thing that are older in 1985 or even earlier than that, and use a fabric tensor defined in this way. Basically, we sum up all these counting normal in all directions that form a second order tensor of Fij here. Okay, and E here represent a density function, probability density function, and then basically integration sum up to 1 here. Okay, and then we define such a fabric tensor, and over all the conjugate along assembly of the granular meter, we can define second order tensor, and then using some special case, for example, a transverse anisotropy referred to when we have a two major principal values, their values are identical, and then we have the special case of transverse anisotropy. And based on this second order tensor, and we can define different invariants, first, second, third invariants, and then this will be this can be used quite a lot in the anisotropic geometric representations of this granular meter. Indeed, in the considered modeling of a granular meter, and also in the micromechanics, even DM, they actually use a lot of this as the basis for their analysis here. So that is the geometric measures here. And also, I briefly introduced the mechanical property of the granular meter. So there are quite a lot, but I wanted to discuss in detail and then here. And so in the civil engineering and in many other engineering, like mining engineering, here we are concerned with the strengths of the granular meter, the supporting structure. For example, as I mentioned before, this power foundation, and they will be supported by the surrounding soil. So the strength of the surrounding soil is important to the power foundation. And so strength refers to the shear resistance due to interparticle friction and cohesion of the granular meter. And also there's another mechanical property called stiffness. Stiffness refers to the resistance to the elastic deformation. For example, we can use a bulk modulus and shear modulus, and then to quantify what is the resistance to the elastic deformations of a granular meter here. And they are functions of this the packing density, grain interaction, and other state variables here. And also granular meter, the flow behavior, the flow, this is a typical property that we describe the solid lag and the liquid lag behaviors and their transition here. And also in some mechanics and in many other mechanics, granular physics, they refer another word property called dilatancy. Dilatancy is a quite interesting thing that is basically unique in the friction material that when we shear granular material, the shearing stress can not only generate a shear strain, but also will generate volumetric changes here. And it typically refer to when we really to get a volumetric increase during the shearing here, right? And that is because the granular materials, they are discrete natures, they are particles, and in the particle interaction is generated by frictional contact. And so that when you shear a granular assembly, the particle will naturally to move over each other, do the rearrangement. And because their shape and other things, and then this rearrangement will naturally cause the change of this void space. And that is we call it dilatancy here. This is quite unique properties of this granular meter. It is indeed is a very core concept, and in some mechanics, and different people develop these considered models. So dilatancy law or dilatancy relationship is the core of many considered models in some mechanics. Anisotropic, as I just mentioned here and mentioned before, is basically indicate this directional dependence of these mechanical properties on the load of the structure configuration, right? And also consider behaviors that basically is that are we want to identify or develop or establish stress strain relations to describe their behavior as a granular meter. And this is typically for not only understanding the behavior of granular meter, but also for practical engineering design, like foundation. So those are the typical mechanical properties that we all would refer to a granular meter. The rest of this today's introduction will quickly go through this computational modeling of granular, the introduction part here. Okay, and then, but before that, we should have a brief history that how the research on granular matter has evolved and over the past several centuries, back, for example, in 1773, and when the Charles Auguste de Coulomb and proposed this law of solid friction in his study of thermal mechanics here. Okay, and so friction is defined in such a way is proportional to the normal force acting on a contact surface, and which is independent of this private contact area here. Okay. And then based on that, further in 1776, proposed this Earth pressure theory, and then which is a foundation of this modern thermomechanics. Indeed, the Earth pressure theory also involve the friction coefficient as very important, or friction angle as very important to done. And this is indeed the early form this the Coulomb theory, right? And also other part like Dick Darcy and propose this Darcy's law of CP, and also the Rankine proposed this Rankine's Earth pressure theory, and which is the further enhancement of this the Coulomb surface pressure theory here. And then in the early in the early 1920s or 30s, the Kartasaki introduced the effective stress principles and the theory of consolidation, and this give us foundation in cell mechanics and make the granular meter research a very important foundation part, both for practice but also for theory. So these are the brief theory and in their part here. And then in the following, after that, in the following like 100 years, and then the mainstream research on granular meter has been based on continuum modeling. So continuum modeling, and then essentially under the researchers want to develop different theories and different models to describe the stress strain relation and other strength behaviors. For example, early days, like 200 years ago, and the Hooke's law, they use this elastic model and to describe it. And later on, you have this the Coulomb model or drug model to describe the frictional dependent strengths of this granular meter here. And then in the 1960s, 70s, and then later on, and then we see a lot of more advanced elastoplastic model, like in some countries we call it clay model or hardening soil model, and also in the German-speaking regions in Germany, in Austria, and a group of scholars they propose this hypoplasticity model, and then to describe the granular meter here. And also in order to describe the flow behaviors of the granular meter, and then there are also very active community working on different rheological models. For example, this very famous mu-I model. And then the different model, in order to be useful really for practical engineering design for different purpose, and normally we need to carefully calibrate the model parameters and implement in a typical numerical method, like finite element method or finite difference method, okay, like flag. And in recent years, more and more people use other numerical methods like material point method or SPH, and then to implement these models, and then to do continuous modeling of boundary value problem involve granular media. So those are the continuum approach here. Okay, and it is basically the discrete element method that makes the granular media research is become more popular and more active in many fields of this science and engineering. And so Professor Rotner just mentioned that this the first paper published by Peter Quendel and Strack in 1979, and the paper was published in Geotechnique. Geotechnique is just for those who don't have a background in civil engineering. Geotechnique is one of the top journals in the geotechnical engineering or civil engineering. Okay, and so the Peter Quendel and Stragan published their paper in a geotechnical journal like that here. And then they developed a code called ball, basically a 2D disk. They use 2D disk particles, and then use this linear contact force model, and then put a typical application to solve mechanics. And the initial example only involve a couple of hundred elements, a quite primitive and then quite simple in that way. But the significance is quite impactful in money, because ever since DM has evolved in such a powerful tool for us to study the granular meter from the mechanical point of view, and then to continue behaviors, and then also further to couple with other methods here. And then here is an example, for example, in order to replicate the Bob-Berenger's strand force chain network observed in the photoelastic testing on the left, and then we can use DM to simulate the different particles to visualize the contact force according to their direction, and also magnitude. And this visualization will have a very good replica of this force chain network observed in the photoelastic here, right? Okay, and so from this one, and then the DM help us really to quantitatively analyze and understand the mechanics in granular media here. And then DMF have further evolved in the three-dimensional one here. And then, for example, if we take just a quick look of the modern days of DM thing, and a lot of researchers tackle the simulation of different shapes and using shapes, including this superquadratics, ellipsoidal shapes, cylinder, and then use smooth polyhedron, and the extended polyhedron, the combinations, and also to combine them together to form a composite shapes, and to tackle different applications and to tackle different type of granular meter. And so the shape has been a major active area in computational granular mechanics. Yeah. And also state of art research is that we can really to use very advanced mathematical ways to represent shape, and then further to discretize the 4DM modeling here. Okay, and then For example, we can nail the popular ways of doing modeling shape in DM, use spherical harmonics and level set Fourier shape describers for non-grid representation or other nerves shapes here. Okay, and this will give us a lot of options where to choose in terms of these algorithms, and also we can choose a different method with different numerical stability and computational efficiency here. Okay, but there are also a lot of changes as we are going to discuss in later lectures that we need to develop more stable and efficient method for irregular particle construction, which can be in contact. Because when you have irregular particles, and then you have to spend a lot of effort, computational wise, also algorithm wise, to develop this contact detection here. Contact detection can be quite a computational demanding in many senses here. It really affects the efficiency of the DM here. And so that is the challenge on this modern shape here. Okay. And in many engineering sectors, the particle crushing and fragmentation is an important topic here. As I show in several examples I showed here, for example, the grading the food grains, okay, and also in the mining and also in the industry and in the stove maintenance, and then we need really to consider this crushing rocks here, and also then in the Antarctic or Arctic explorations, and then this ice breaking boat, and then we need to deal with this ice, how to break the ice shape here. And also the landslides can be one thing here. And also in the railway engineering, and then this how to deal with the continued crushing of this we call it ballast, and then underneath these railway tracks, and because the continuous loading by the trains, and then when you cross it, their mechanic behavior will change, and also meanwhile it can cause very significant settlement, and this will affect the operation and safety of the trains here. And this is the important part we need to consider the particle crushing here. That's why I mean another very active area that in DM related to how we can deal with the particle crushing and or fragmentation here. The easy way is that we do this called a particle replacing method here. We have a bigger sphere particle. Once we determine the crushing criterion is met, and then we let go to turn into a number of smaller particle. We can consider equal size of a certain grain size distributions to replace, and we can really consider, for example, the total mass conservation in such way. So we essentially we replace a big particle with a number of smaller particles with different size, and this is what we call a particle replacing method to consider the crushing here. And there are also a couple of different applications of this method for this, for this the crushers in the mining engineering, and also like in this study of the in the real engineer for the blaster. And again, that Peter Kondo and his collaborator and proposed this another similar work in 2004. We call it BPM, the bounded particle models, and for implementing the DM. Basically, they implement a parallel bond and to connect the particle together, sphere particle together, and this bond can sustain certain kind of strengths, including the stretching and then twisting, and also the compressive strengths. Once the strength is exceeded, and then the bond can be broken, and then in this way they develop a capability to model this fragmentation part, especially for in rocks here. And so this is a further illustration that they implemented in a 2D, PFC 2D, and it's also PFC 3D, different version here. Right? And so here's some just some examples of further research works along this Islam research using this BPM model here. And then another LAMP work that are essentially to consider a single particle can be crushed, but before the crushing, we can really use a other method, like a finite element method, to describe the particles into different mesh, and then use FEM to analyze the crushing behaviors of the individual single particle. And this is what we call FDM here. Indeed, a typical figure is Minjizar. It proposes this FDM. FDM, F means finite element, DM means discrete element here. Essentially, is a finite difference, finite element method and discrete element coupling. You see. So the coupling is discretize each individual single particle by DM, and then that is crushed in such a way. And then, but you can really put a lot of particles together, use DM to simulate their frictional interactions between each other here. And these are the some further examples I showed here of the using this FDM to really for the simulation here. In a sense, modern day Granular media modeling, and they are trying to understand some quite fascinating natures of Granular media. And one nature is multi-scale. Multi-scale in terms of, as I showed before, including both the grain size and the grain shape here. Okay, and then at the different size, at different shape, and then you could have quite multi-scale features. And also at the particle scale, and then you also need to consider like a engineer scale, how we can relate to the particle scale behaviors of the grain meter and with the engineering performance, like a slope, engineer slope, like also the railway track here. Okay, and so those are another multi-scale features here. Okay, so another thing is would be that in a lot of engineering settings that we need to deal with this the coupling process here. We know that grain meter itself, and then it's a pulse meter, and then in between the particles, and there are a lot of pulse. Pulse can be filled by liquid, and even by the mixture of liquid and air here, right? So it's a multi-phase material, and then this kind of mixture have a lot of different unique properties, and then we have to deal with here. That's why the modern day computational geomechanics, granular mechanics is dealing with to tackle the challenge posed by this multi-scale and multi-phase natures. And then they develop different numerical methods to couple together to model this multi-scale and multi-physics nature. Yeah. For example, just give you some further examples now how they have done. They wanted to simulate in mechanical engineering to test the mechanical performance of a certain material, and then which is granular based. Okay, and in the geotech engineering, we want to test the soil behavior, soil strength, and also the constituent behaviors, and we can use DM here. Okay, in the chemical engineering, and when we have a rotary drums, we need to look at this the mixing of this grading, and then we can use DM to do that here. And also in the agriculture, and how we can to model and evaluate such a processing, and then we can do that. This is what Professor Redler just mentioned, that how the tire soil interaction can be very important application, not only on Earth, but also, for example, when you send rovers on Mars and the Moon, and you have to also consider for such a typical application here, right? And in mechanical engineering, I want you to do this karting and also other process, and this we can use the DM and other numeric tools for that purpose to understand the behavior of the grind media here. We can transport the bulk material like soils, like other grinder grains, and then we can also consider like the ash and other flows here. These are the ash simulation here. And then I want to go back to this so-called force transformation in grind media here. Okay, indeed, the bearing capacity and a lot of mechanical behaviors are closely related to the force transformations. That showed on top. Again, this is the photoelastic observations. As you can see, this gives us not only a clearly show a strong and a weak force chain, but another important feature is the strong force chain is not persistent. They can be, we call intermittently established and a decay of the strong force chain. And when you have a strong force chain collapse, and there will be in neighboring regions, there will be another new strong force chain formed. And so in this sense, that how the grind meter sustain the continuous shearing process in a quasi-static or in a dynamical process here. On the bottom is the DM simulation that we can simulate it here. And then here is another illustration that the grind meter essentially sustain external load or through this a very unique force transmission mechanism here. And this figure plotted by Stefan Luding, and in a Nature papers that you have a certain limited region and direction where you can really to allow this the grind meter transfer the external load in a more effective way. And this applies for both a static mode and also a dynamic load here. Okay, and so the on the right, basically the cartoon shows that force chain can be broken and can collapse. And this is the application that I want to relate to the previous railway station here. And then how we can evaluate the performance of the railway tracks, the ballast supporting these railway tracks. And then we can really to use the DM to simulate such a supporting structure and to evaluate or assess their performance subject to this repeated train load here. And also, the DM or the other tools can help us to understand the performance and for the design of this planetary rovers and how they land, how they move on the other planet. And these are the examples. People also do some kind of a physical test on the on land as well, but it's not ideal. And we can supplement with the numerical model like DM to really test when such a lander, Mars lander, and land on different soils with different density, and what would be the optimal design for that here. Okay, I also wish to have a quick we have a quick review of the popular software packages, especially DM, and then we can make use. And if you have further interest, then you can really explore here, for example. And the commercially we call pre-proprietary code, and a commercial software. Popular one would be including this Itasca's PFC 2D and PFC 3D. Okay, and then you can explore their capability and then for different use here. And also, UDEC is another product by Itasca. Typically, they use that to simulate the block-like material, like rocks and or fractional rocks here. Okay. And then EDM probably the Professor Ratna mentioned before that the hand-on tutorial example sessions you actually use this EDM really to for hand-on experience using for simulations. And indeed, EDM has been quite a it's called expert in DM, as you can see here. It has quite a wider range of application around the world in different applications for the vehicle road interactions, like especially for the chain-like vehicles, and for the excavation for the mining industry, transport and the conveying of these bulk materials for the conveyor belt, and for this agriculture application here. And Rocky is another granular, another DM. And then, as you can tell from the name, Rocky itself was initially dealing with the handling of this rock mining like material here in this crushing process, and then how to do that. And later on, they further extended to the normal DM capabilities for that here, which you can use, you can make use of. Yeah. And in addition, these are the quite popular commercial software that are you can use. And then on top of that, and we also have options really to use different open source or free software here. For example, Lance is a open source software that we can use. It's basically developed on top of this the Sandia National Labs the LAMPS software, and they add up this fictional context concept, and then also now they have the capability to use the GPU acceleration to simulate larger scale granular system. Yeah. And it is another open source software have a very larger community now using it, and it's open source have a lot to develop and keep continuing maintain and develop, extend the capability, and then you can really to search the word and then to download and try it if you like it. And Mercury DPM and is another, I don't know, it's open source now, and then developed by the researchers in the University of Twente, and then you can use that for the purpose here. There are also other open source, like this CDM is basically the normally for the rock engineering, and then for the break of rock slopes and rock blocks into different part here. Okay, and this DMMS basically for the very larger scale chemical engineering, that's like fluidized bed and other simulation, and also they have this capability really to couple with this fluid like air and liquid here. And also this DM lab is another kind of specialized DM here. The cosine is a coupled code, and they can simulate different coupling process here. And then CytoDM is another open source software that we developed in our group that we can use different irregular particle shape and to for DM simulation here. And you can really search the name and then to download the package to try. And also there are other specialized DM like agriculture COE for agriculture applications, and a MetaDM and a specialized development in the environment of the MATLAB, and then for a high performance computation. And also, I want to mention there's some popular academic journals, and you can refer to the latest publications and research on this one, for them including granular matter, the powder technology, advanced powder technology, computational particular mechanics, and also some physical journals, including Physical Review A, Physical Review Fluid as well, and also soft matter, and CMME, IGSS, and JMPS, and also my journal. Indeed, we publish a lot on this granular media, granular mechanics research here. Also here, I list some kind of typical recent textbooks, and you can also refer if you want to have a quite systematic read on the topic of this granular material here, including these are published in 2020, 2016, 2015, 2 books here, and also more books by different authors here. Okay, and they could have different focus and emphasize on the different topics. So here. So this is a quick introduction. I want to give you, just supplement what Professor Ratna just mentioned as the first part of this introduction here. So in what following the following 5 days, and among 5 days on Wednesday and a part of this Thursday, on Friday, and then I will mainly cover, as I mentioned, the multi-skill and multi-fixed nature of the granular media, how we can develop proper numerical tools, and develop suitable coupling schemes really to consider these 2 important natures here. I'm going to use different background problems to demonstrate, for example, in the geomechanics, and also in any advanced manufacturing, including 3D printing, and also in the pharmaceutical industry, that how we can really to compact the powders into a medical tablets. These are examples to show that the challenges, to show how we can really tackle the challenge by using different advanced numerical methods to simulate their behavior here. I use the last 2 slides just demonstrate what are the multi-skill natures here. Okay, as I showed from the figure here, you typically for a granular media in a civil engineering, and then we have a typical sand here. Sand particle typically is a sub-millimeter, like 1 millimeter to even 0.1 millimeter. That's sand here. You put them together and they seem so simple, but you put so many of them together and then they can form a foundation that support a skyscraper, a high-rise building of like 200 or 300 meters tall here. Okay, and then if without proper understanding of their behaviors, and then you could cause a major hazard like this one here. This is a newly finished residential building collapse, and just because that the contractor of they don't have a sufficient knowledge that of this understanding of the granular mechanics here and soil mechanics here. Okay, and also we in many areas wanted to prevent this natural disaster, and their length scale can be several hundred meters and to up to several kilometers here. Okay, and so you can tell from this simple geotech engineering application how we can understand their particle scale from micron to sub-millimeter scales, length scale, to a kilometer scale length scales, and their length scale range, and to understand this multi-scale nature, and to develop proper ways to bridge the different scales, and bridge not only their mechanical behavior but also their hydraulic behavior, because they're power, water, and other behavior. That can be quite a challenging way to understand it. Another feature would be what we call multi-physics here. As I mentioned before, their granular meter are typically pulse meter. This pulse is not fixed. So for a lot of pulse meter, we refer pulse meter as we have fixed pulse, and then by the solid matrix. And then that may be a little bit easier than this granular meter. Granular meter itself refers to more general in a way that the particle can move. And the move and the pore can change. And so that in the pores, you can have water, you can have air, you have a mixture of them. And then also you can really have a reactive fluid like a acid and other part here. Okay? And so this mixture of this the different fluids and with the particle mobile particles, this will create quite a complex multi-physical spin phenomenon here. Okay, and then for example, as I showed before, that only at a proper water content you can make a very tall sand castle on the beach. But if you use less water, and then you cannot make the stand. If you add more water, and then this will collapse as well here. On a suitable water content can make a standing sandcastle here. Okay, and then you can form a dry sand pile on a level ground here, but add some water, and then you can really form the higher here. Okay, and then also in the urban development in the typical city like in Hong Kong, and then land shortage will push the government really to develop new land. They normally go to this land reclamation, use a dredging technology. And then the dredging process involves action of these granular particles and with the water, environmental water here. And then this is an important application. And also in the dam engineering, and then especially in the earth embankment dam, and then we needed to pay a lot of attention to this piping phenomenon. There are small pipe and developed, and this at a certain suitable hydraulic gradient, and then small cell particle can be carried out and through the big pore for big pores, and then when this more fine particle is carried out, and then this pipe can be enlarged, and then make the whole embankment dam collapse here. This indeed at the bottom is one of the example I showed here. After this, the piping formed, and then you basically make a whole dam collapse here. And also in offshore engineering, and then when we evaluate the offshore platform stability, and then we need to consider the seabed soil interaction with the different structures. And also when we do this the offshore and extraction, and then we need really consider, for example, the missing hydrate extraction, and their phase change can be very important features here, because this is so-called gas hydrate is a quite special kind of chemical components. Only at a suitable combination of temperature and pressure, they can exist in the solid state. And any disturbance on the temperature or pressure, they can change to a gas lag. And then they typically are located in the seabed, in the shallow, some depth of seabed. And when they really become a gas lag, and it can cause a collapse of this sediment, and cause a very large scale, we call it submerged landslide here. This landslide can really cause a damage of this offshore platform, and also cause a generator wave, even tsunami. So these are the typical multi-physics phenomenon. And these are I use this example to show that in the civil engineering, in the general in the geotechnical engineering, that we could relate to encounter such multi-physics problems. But in many other engineering, like what I'm going to show you in later lectures, in the metal 3D printing, that we need to handle this multi-physics properly and rigorously to capture the physical process, and then to replicate the phenomenon, and then to develop a very robust tool for the 3D printing to done here.
Hi, it's a very interesting presentation. My question is, like as a PhD student, which DM solver or a software should I start with? There are a lot of options So should I go with a commercial one? Should I start with an open source? Or how should I get started with DM?
Well, really depend on your need here. If you really pure on a application, you want really to work on problem, and then you want to get it fast and to build up the model, and then probably you can really use this like EDM, as Professor Ratna will show you later on this, and or you can use this even PFC, and that's quite easier because they have a very good documentation and tutorial examples for you to start with, and then you can also get technical support. And so that is on a pure application point of view. If your PhD research is on application to solve certain problems here, but if your research involve a lot of further development, for example, you wanted to develop a coupling with different processes with granular particle, and you probably wanted to use open source one. Okay, for example, this it and is would be a good starting point because their user community is pretty big, and then I think in Europe there's a big community that is they based on using a it, which means that with such open source you can really access the source code, and you can really to do some further coding to implement your own functionality in it, and then if you encounter any problem, you can really to communicate with this the other users, and then to get it solved. So it really depends on your need. There's no gold guideline that which one is the best.
So for agricultural tractor application, so the force is applied through the tractor tire over the soil. Can you elaborate in that?
This is just an illustration of this, like a point force or dynamic force when we impact on a ground here, it generates an elastic wavelet here. For this agriculture applications, you have a vehicle like this one, right? And essentially, the whole thing is about the interaction between the tire with the soil here, right? Like this example I show here, okay, and typically, and so essentially this is how a tire terrain interaction problem, and where we wanted to have sufficient soils, simulated soils as a granular meter layers, and then you wanted to track this the tracks, how the tire develop enough tractions and through this friction, and then to for that purpose. So as the previous illustration of that point load is just an illustration of how the force transfers would be typically, but it does not really to directly relate to this frictional interaction of this tire with this terrain thermal mechanics. We can the terrain thermal mechanics here. Okay, is a what we call the soil wheel interaction problem here. They are different.
So I wanted to ask, when it comes to melting of granular material, so what approach should be a good approach? So for example, when we use additive manufacturing, we melt the metal powder via laser. So what process you would recommend? Like what coupling with the DEM, and what would be your recommendation on this?
You want to melt a
Yes.
metal powder. This not Wednesday. This could be Thursday. I'm going to present my lecture will be on how we use the coupled CFD-DM to simulate the melting process of these metallic powders, and to do that.
Thank you so much.